Alright, welcome back guys. We'll finish up 9.4. We were working with evaluating these logarithmic functions. I showed you how to think about it mentally, to do it by hand, and then also how you can utilize the calculator. So now we're going to finish up. We're going to talk about this change of base formula. Okay. So this might arise in situations where, for example, what if we did not have this this log function here that allowed us to change the base? Okay, see how we can put in our own base? If that option wasn't there and we only had these two logarithms or logarithmic functions, then how would we evaluate log base 3 or log base 5? Okay, so this change of base formula allows us to actually do that. And if you look at it, it says if you have log base b of m, so if you have a logarithm of base b, then you can change the base to evaluate this. You can use log base a. But you have to do it this way. You take log base a of the argument, okay, and divide that by log base a of the old base. Okay, so you're using another logarithm here, and you're taking the log of the argument and the old base. Now typically the logarithms that are used are either the common log or the natural log, because we have those functions readily available. Okay, so it allows us to evaluate. I know you can do it directly now, but it would allow us to evaluate something like log base 6. Okay, because if we only had access to the common log and the natural logarithm, then how would we do one like this? Well, we use this change of base formula. Okay, so what you do is, and you can use technically you can use any base logarithm, but like I said, the common log and the natural log are most often used. So I'll show you both ways. You could say the common log of the argument, which is 10, divided by the common log of the old base, which is 6. Okay. And you could plug this into your calculator. So the common log of 10, that's going to be 1 if you recall, divided by the common log of 6, and this is actually going to be an irrational number. It's going to be roughly, if I carry this out to 4 decimal places, 1.2851. Okay, it's roughly equal to that. Log base 6 of 10. Okay, but I want to show you that you could also use the natural log, and actually lots of times this is the more common thing to do. But I'll show you we'll get the same value if we use the natural log. So we're just using a different logarithm with a different base. That's all. Okay. And we get the same thing, don't we? Okay. Alright, well that's basically the utilizing the change of base formula. Okay. So it doesn't matter what the argument in the base are here. You can use either the common log or the natural log to change the base and evaluate this logarithm. Alright, now the second to last thing we're going to do is look at converting between logarithmic and exponential equations. We've actually already done this when we evaluated those logarithms. Okay, well, like if we were trying to find log base a of x, we just had to remember this inverse relationship right here. Okay, that x would be equal to a to the y power. That's how we evaluated a logarithm. So knowing this, that these two statements are equivalent, we can convert an exponential equation like this to a logarithmic equation, or we can go in the opposite direction and convert a logarithmic expression or equation to an exponential equation. Okay, so that's what we're going to do now. Well, the way I think about this, guys, when I'm starting out with an exponential equation, the base is going to stay the same. In fact, it's going to become the base of your logarithmic equation. So I go ahead and I just write out, well, this will be log base 125 of, and then you got to put something here for your argument, and then this will equal something, okay? And then I just think that, well, the logarithm is an exponent, so the exponent is 1/3, so that's what this logarithm has to equal, and so the argument has to have been 5, okay? And if you recall, anytime the argument of your logarithm is smaller than the base of your logarithm, then you're going to get a fraction, okay? All right. Or another way to think about this is just swap the 5 and the 1/3 and add a log here on the front, okay? And the 125 becomes the base. All right. Example 12, it says convert to a logarithmic equation. Well, I'm going to do the same thing. The base here is p, so that'll become the base of my logarithm. And then this will become the log base p of k is equal to 3, okay, because 3 is the exponent. All right, so that's how we convert exponential equations to logarithmic equations. Now, what if we want to go in the opposite direction? Well, it's very similar, okay? Whatever the base of the logarithm is, that will become the base of your exponential equation. So this will become n to the power of negative a, and then this will equal v. In other words, you can think about it like just throw away the logarithm and then swap the v and the negative a. Swap these two numbers. And then this final example here, excuse me, example 14. To do this one, we have to remember that the base of a natural log is e, even though it's not written. Okay, so to convert this to an exponential equation, the base will be e, the power will be 2.9957. I think we saw this previously, didn't we, in the part 1 video? And this will be equal to 20. All right. Now you may be wondering, why are we doing this? Like, what's the advantage here? Well, ultimately this will allow us to solve logarithmic equations when we get to section 9.6. So that's kind of why, that's the motivation here behind this. If we have a logarithmic equation, sometimes it's easier to solve by converting it to an exponential equation. All right, so the last thing we're going to do is talk about graphing, okay? And I showed you just a generic graph, or a general graph of a basic exponential function versus its inverse, which is a basic logarithmic function, okay? And we see that symmetry here, don't we? Let's actually try to do one by hand, okay? So, example 15, we want to graph log base 3 of x, and we also want to graph 3 to the power of x. So one of these is an exponential function, and then the other one is a logarithmic function. Okay. Well, to do this, guys, because if you're doing it by hand by using a table, sometimes it's hard to think about, well, what values of x should I choose? It's not as simple as just choosing 0, 1, 2, 3, 4, okay? So sometimes it's easier to think about this by first graphing the corresponding exponential function. Okay, so you notice here the base in both of these functions is 3. So if I were to graph 3 to the x first, that might give me some insight into graphing log base 3 of x. So that's what I'm going to do first. And for this, because we're just plugging into the exponents place, I will just choose these values. Okay, I think that's as many as I'll go. All right, so think back to 9.3. 3 to the negative second is the same as 1 over 3 to the positive second, which is the same as 1/9. Okay, so get the ordered pair -2, 1/9. And when I plug in -1, 3 to the negative first power is the same as 1 over 3 to the first. Okay, which is the same as 1 over 3, or 1/3. So this becomes -1, 1/3. And then, of course, if we plug in 0, anything to the 0 power is 1. So again, we're going to see this exponential function cross the y-axis at 1. And then if I plug in 1, we can probably do these in our head. 3 to the first is 3. We get 1, 3. And then 3 to the second is 9. So 2, 9. Okay. And I'm going to go ahead and plot these ordered pairs. -2, 1/9 is just a little bit above the x-axis. -1, 1/3 is a third of the way up. 0, 1, that's where this function crosses the y-axis. And then we've got 1, 3, and 2, 9. Okay? And so we get that basic exponential graph, don't we, or curve. And this is an increasing function because the base is 3. All right, now what I'm going to do is, because this log base 3 of x, this is the inverse of this original function. So what I'm going to do now, knowing that they're inverses of each other, I'm going to choose these values, the outputs of my exponential function, to be the inputs of my logarithmic function. Okay, 1/9, 1/3. That's what I meant previously when I was saying you have to be more strategic about the inputs for these logarithmic functions. Okay, all right. And basically what we're going to get is the old x values for our exponential function. Those will become the y values, or the function values of our logarithmic function. But just to show you, if you were trying to figure this out, log base 3 of 1/9, well, you're trying to figure out 3, to what power is equal to 1/9. Well, it's the negative second power. We actually saw that over here, right? Okay. Now you could do it by hand and say, well, 9 is the same as 3 squared, so this would be 1 over 3 squared. And then 1 over 3 squared is the same as 3 to the -2, okay, if you work it out fully. And then similarly with 1/3, log base 3 of a third would be equal to -1. Okay, so again, you'll notice the x and y are just trading positions, aren't they? And then log base 3 of 1 is 0, because you're asking yourself, 3 to what power is 1? 3 to the 0 power. Okay. Oops. Okay. All right, and then log base 3 of 3, well, that's just 1, because 3 to the first is equal to 3. And then finally, log base 3 of 9 is 2, because 3 squared gives us 9. So hopefully you're kind of developing a little bit of intuition in working with these logarithms, because these can be challenging to kind of wrap your mind around. But now if I plot these ordered pairs, guys, on this graph here, I only go to the right a ninth of the way, and then I go down 2. Okay, so this one is barely to the right of the y-axis. And then 1/3, -1, well, that's a third of the way over, and then down 1, so a third of the way to the right of your y-axis, and then 1, 0, that's the x-intercept, or that's the 0 of this function. 3, 1 will be here, and then finally 9, 2. And so if I sketch the graph of this logarithmic function, it is a mirror reflection about that, remember that imaginary line, y equals x. Okay, if I were to have graphed them on the same coordinate system, these would be reflections of each other about this line right here. So again, let me just summarize some of the characteristics. So the range of an exponential function is from 0 to infinity, not including the 0, and that becomes the domain of your logarithmic function, from 0 to infinity, but not including 0. Your exponential function crosses the y-axis at 1, and your logarithmic function crosses the x-axis at 1. Okay, so those are just some general characteristics. Now I want to graph these in Desmos to show you. I'm going to turn off some of what I've got in here. Okay, just come down here. Okay, so I'm going to type in y equals log. Let's see. Okay, so to put in the base, you need a subscript. So you have to hit Shift and then the dash key. Okay, and then 3. And then scroll to the right and then put x, and that gives us our logarithmic curve. And then beside that one, I'm going to graph my exponential function, which is 3 to the x, and there it is. And while I'm at it, guys, I'll go ahead and graph that line of symmetry, y equals x, and there it is. Okay. So you can use Desmos to graph any of these functions. Let's try a couple others, because there are some in your homework. What if we wanted to do the natural log of x? Well, there it is. Okay. You'll notice all of these basic logarithmic functions will always cross the x-axis at 1, because any base to the 0 power is 1. It just, depending on what the base of the logarithmic function is, determines how fast these functions increase. And by the way, these are all increasing functions. Let's try another one. Let's do log base 2 of x. Okay. Log base 2 there in black. Now let's do y equals log base, let's do log base 5 of x. Look, interestingly, the larger the base, kind of the more horizontal the function becomes, or more kind of pushed down. Now let's do one more. Y equals, let's just do the common log of x. There it is in blue. See that? And the reason is because think about the corresponding exponential functions. How when the base gets bigger, the function gets steeper. You guys remember that? How it gets steeper? So here, the larger the base for the exponential function, the flatter it gets. Anyway, the last thing I wanted to show you or kind of talk about was, what are these logarithms used for? Well, one very common use is in scales. Okay, when you have data that increases exponentially, then typically they'll use a log scale. And I'm going to give you some examples. Okay. The pH scale. Okay, so in chemistry, the pH scale actually measures like the number of hydrogen ions that are in solution. Okay, and so something that has a pH of 0 is said to be neutral. That just means it has as many positive hydrogen ions as it has, I think they're called hydroxyl ions. Basically, it's like the water molecules split up. So you have like a positive and a negative ion. So anyway, at a pH of 7, you have just as many of positive and negative ions. But then the more negative ions you have, the more acidic the solution is. That's actually how you define what it means for something to be acidic. And so you have this scale. So let me well, I can't write on this because it's a website. I should have taken a screenshot of this. But anyway, each of these little color swaths here is like an increase in pH. Okay, so 7 is kind of right here in the middle. When you go to the left, you become more acidic, more negative hydrogen ions. When you go to the right, you become more alkaline or more basic. And so when you come over here, so 7's in the middle, here's 6, and then here's 5, here's 4, then 3, 2, 1, okay? But what's actually happening is the number of hydrogen ions is not increasing linearly. It's increasing exponentially, okay, by 10. So when you say something is, each increment is an increase in a factor of 10 or a multiple of 10. So something that has a pH of 6 versus something that has a pH of 3 is 10 to the third times more acidic. Each time you come to the left, you're increasing the number of hydrogen ions by a factor of 10. So 10, then 100, because 10 to the second is 100. 10 to the third is 1,000. 10 to the fourth is 10,000. Okay. So one change, one increment in a logarithmic scale can actually be a fairly large change. And then the same thing happens as you come to the right. You're just talking about a solution that's more basic or more alkaline. In this, if you look here, it says, for example, a substance with a pH of 4 is 10 times more acidic than one with a pH of 5, and 100 times more acidic than one with a pH of 6. Okay. All right. Another example is the decibel system that we use to measure the intensity of sound waves. Okay. This is a log-based scale. I can't remember if it is a log-based 10 scale or not. I don't remember what the base is. But anyway, just a small change in the decibel scale can actually mean a significant increase in the intensity of the sound wave. Okay. Another scale is the Richter scale that we use to measure the intensity of an earthquake. And the Richter scale, I actually always thought it was, I always thought it was a base 10 scale, but looking at this over here makes me think that it's like a base 3 scale, because each of these, when you go from a 4 to a 5, it looks like you're increasing by a factor of 3, or from 5 to 6, you're increasing by a factor of 3 there. But anyway, if you look here, well, yeah, it says a tenfold increase in amplitude. So it's the amplitude of the seismic waves. for example, an earthquake measuring 7 is much stronger and more destructive than one measuring 5. Okay? But it's kind of exponentially more destructive or stronger. And then finally, one thing, stellar magnitude scale. This is something I'm fairly familiar with because I used to do astrophotography, and so things in the night sky, they have a magnitude, or they're on this magnitude scale. Okay, well, this is another log scale, because the reason is, how would you compare like the brightness of the moon or Venus with the sun? Well, the sun is so many more millions of times more brighter. Okay, so you have to use a logarithmic scale, and I think this is like a base 2.7 scale. So when you say, so like Venus right here is, I think it has a magnitude of like -3, and then the moon over here, it looks like it has a magnitude of, I don't know, -12 or -13. But a change in magnitude means an increase in brightness of like 2.7 times. Okay, and then on the other side, something that has a positive magnitude, the more positive you get in magnitude of an object in the night sky, then the fainter it is, or the dimmer. Okay, so typically objects in the night sky that have negative magnitudes, you can, well, some of them you can see. You have to get I would say most objects with negative magnitudes you can see, even in the light polluted city. But some of these other objects, so look, if you look here, faintest naked eye star is around maybe -5. So to actually, or not -5, but +5. So to actually see that, you'd have to be under a very dark sky. You wouldn't be able to see it in the city. Okay. But anyway, these logarithmic functions are used a lot to scale quantities that increase exponentially. So anyway, those are just some examples, common examples. All right, so that's it for 9.4, guys.